The linear correlation coefficient, which is more formally called the Pearson product moment correlation coefficient, is a measure of the strength and the direction of the linear relation between two quantitative variables. So this calculation is going to measure, first of all, the direction. Is it a positive or a negative association? And what's the strength of it? Is there a strong linear relationship? Is there a weak linear relationship? Is there no linear relationship? So that's what the linear correlation coefficient is going to do for us. Now, for every kind of calculation, there are two. There is a parameter and there is a statistic. In this class, we're only going to really discuss the statistic. We're not going to really do anything with the parameter for the correlation coefficient. Now, the Greek letter rho kind of looks like a funky P, but it is a Greek letter. If you write it, you kind of start at the bottom of the P, come up and curve around. So that is rho. So whereas a P, you would do it like that, right? So it's similar to a P, but not exactly the same thing. Anyway, that represents the population correlation coefficient. So rho is the parameter. The letter R represents the sample correlation coefficient. Using our normal standard, we use a Greek letter for the parameter. We use a English letter for a statistic. So R is going to be the sample correlation coefficient. In this textbook, we present only the formula for the sample correlation coefficient. So we're not going to worry about rho in this class. We're only going to worry about R. And here is that formula. This is the conceptual formula. There is an equivalent formula that is a computational formula. But if you look at that, that doesn't look any nicer than the conceptual formula. But the arithmetic would probably usually be easier using this formula. But I'm not even really going to discuss this formula. We're just going to discuss this, and we'll use technology most of the time. But anyway, I want to discuss it. What's going on in this formula? So sigma means what? So we're finding a sum, we're adding. Well, what are we finding the sum of? We're finding the sum of this stuff that comes after that sigma. So here we have x sub I minus x bar divided by s sub x. So that's in parentheses. We're going to find that. So x sub I is representing the x value in our data point. X bar is the mean of all the x's. S sub x is the standard deviation of all the x's. So like, for example, for the golf problem, if I pull that back in, I'm not going to do this one by hand, but if I pull that back in, so like x sub 1 would be the 100. So I would take 100 minus x bar. X bar would be the mean of these speeds. And then I would divide that by s sub x. That would be the standard deviation of these speeds. Then I'm going to take y sub I. So that would be the y value. So the first y value would be 257. So I would take 257 minus y bar. That's the mean of all the y values. And I would divide by s sub y. That would be the standard deviation of all the y values. And so again, I'm going to do that for each point. So when I use 100 for x, I use 257 for y. When I use 102 for x, I use 264 for y, and so on. I'm going to multiply those two things together, add them all up, and divide by n minus 1. That gives me the calculation for this correlation coefficient. One more thing. Have you ever seen that formula right there before in the first set of parentheses? So this right here, when I calculate that, that's the z-score for the x value. So this right here is the z-score of the x values. This right here is the same formula. the y value minus the y bar divided by s sub y. That's the z-score of the y value. So what I'm doing is I'm finding the z-score. Like I'm going to find the z-score for 100. I'm going to find the z-score for 257, and I'm going to multiply those two things together. Then I'm going to find the z-score for 102, the z-score of 264, multiply those two things together. Z-score for 103, z-score for 274, multiply those together, and so on and so on and so on. Once I have all of those products, then I'm going to add them up and divide by n minus 1. So I'm essentially averaging. We're dividing by n minus 1 for the same reason that we did that with standard deviation and variance back in chapter 3. We're dividing by the degrees of freedom. So why do we do that? So here's the idea. Now this is just made up, right? I'm just making up some points like this, right? So my x values range from here to here. If I were to find x bar would be somewhere along here in the middle. And my y values range from here to up here. If I were to find y bar would be somewhere around here in the middle. And so like this line here would be representing x bar. This line here would be representing y bar. So in this calculation again, what I'm doing is I'm going to find the z-score for the x values. So like, for example, if I pick this value right here, the z-score for x is measuring how far this value is from x bar. So this would be my z-score for the x value. And if I find the z-score for y, that would be measuring how far this point is from average on the y. So every one of these points has a z-score for x and a z-score for y. Now, if I have a point that's up here, so like the x bar and the y bar kind of divides this into 4 parts. Up here, over here, down here, over here. Now, if I have a point that's up over here, then that point is going to have a positive z-score for x. The z-score for x would be positive because that point is bigger than average. So when I take the point minus x bar, divide by s, that's going to have a positive z-score. Likewise, because this point is above y bar, the z-score for y would be positive. All of the points up here will have positive z-scores for both x and y. So when I multiply the positive z-score for x times the positive z-score for y, that's going to give me a positive product. Likewise, when I have a point down over here, the z-score for x will be negative. The z-score for y will also be negative. The z-score for x will be negative because this x value is smaller than x bar. The z-score for y will be negative because the y value is smaller than y bar. But when I find the product, when I multiply negative times negative, that's going to give me a positive product. So any points up here or down here are going to give me a positive product. Now, if there happens to be a point over here, the z-score for x would be negative. The z-score for y up there would be positive because the y value is above y bar, but the x value is below x bar. So when I multiply the positive z-score for y times the negative z-score for x, that's going to give me a negative product. Any points up here will have a negative product. In the same way, any point down here, the z-score for x will be positive because the x value would be bigger than x bar. The z-score for y would be negative because the y value is below y bar, and so I would get a negative product. So when I find all of these products and add them up, if most of the points are down here and up here, then there'll be more positives than negatives, and I'm going to get a positive correlation coefficient. If most of the points are up here or down here, then there would be more negatives than positives, and so I would end up with a negative correlation coefficient. So that's indicating whether I have a positive association or a negative association between the two variables. Now, if there's an equal number of positives and negatives, then all of those will cancel out, and I will get a value close to 0. A value close to 0 will indicate that we don't really have a linear relationship. Now, again, I don't want to leave out the fact that I add those all up. So I add up all the products, and then I divide by n minus 1, and that gives me the correlation coefficient. And again, mathematically, I'm not going to really do this, but mathematically, this and this happens to be equal. So what is this saying? This says take all the x coordinates times the y coordinates and add them up. And then from that, take all of the x coordinates and add them up, take all of the y coordinates and add them up, and multiply those two answers and divide by n, and subtract it from this. Take that and divide it by this mess. So this mess is take all the x values, square them, and add them up. Take all the x values, add them up, then square the answer and divide by n, and subtract those two things, and then square root that. Do the same thing for the y's. Take all the y's and square them, add them up, minus, take all the y's and add them up and square the answer and divide it by n. Do that subtraction and take the square root. Multiply the two square roots and do this division, and you get the same mathematical answer. So again, on the face of it, it doesn't really look like this is easier than this, but the arithmetic is usually easier for this than this. And so that's why I even bothered showing it to you. So we're going to calculate a correlation coefficient by hand in just a minute, and we'll do that one time, and then from then on, we're going to let technology find the correlation coefficient for us. Before I do that, though, I want to talk about properties. We're going to calculate this correlation coefficient. So what? What's it really doing for us? Well, the linear correlation coefficient is always going to be some value between -1 and +1 inclusive. That is, -1 is less than or equal to r, which is less than or equal to 1. So it's impossible for the correlation coefficient to equal 2. It can't happen. The biggest thing that the correlation coefficient can ever be is 1. The smallest thing the correlation coefficient can ever be is -1. So you'll always get a value between -1 and +1, inclusive. Now, if r equals +1, that means we have a perfect positive relation that exists between the two variables. So for example, if I have data that's in a perfect straight line so that we would have a positive association, this would be a case where r equals 1. So if r equals 1, we have a perfect straight line of data, and it's got a positive association. If r equals -1, then there's a perfect negative relation that exists between the two variables. So if I have this set of data, when I plot it, it's in a perfect straight line, but we have a negative association. In this case, r equals -1. Now, how often do you think we get perfect in real data? Not very often. So normally, we're not going to get r equals 1 or r equals -1. Instead, we're going to get something in between as a general rule. So number 4, the closer r is to +1, the stronger is the evidence of a positive association between the two variables. So if r equals something close to 1, that's going to indicate that we most likely, there's strong evidence saying that we have a positive association between the two variables. And more specifically, we have a positive linear relationship between the two variables. The closer R is to -1, the stronger is the evidence of a negative association between the two variables. So like if R is -0.9, that's pretty close to -1, that would be stronger evidence that we have a linear relationship than if we had, say, R equals -0.8. The closer it is to -1, the stronger is the evidence. If R is close to 0, then little or no evidence exists of a linear relation between the two variables. So if we have data such as this, where there's no positive or negative association, for example, in this case, R would be close to 0. Now, I do want to emphasize the word linear here. So if R is close to 0, that doesn't necessarily mean there's no relation at all. That just means there's not a linear relation. So like, for example, if we had this graph, in this graph, R would be fairly close to 0, probably. But there is a relation here, maybe. It's just not linear. The linear correlation coefficient is unitless, so the unit of measure of X and Y plays no role in the interpretation of R. R does not have units. And last but not least, number 8, the correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. In fact, generally it will. Not only could it, it will. The question, I guess, is how much. But it could substantially affect the value. So for example, suppose if I had a set of data that looked like this, R would be close to 1, right? But if I then have a data value, say over here, so most of the data here are following this very straight pattern, but then I've got this one point that doesn't follow the pattern. That one point could affect the correlation coefficient. So instead of R being close to 1, R could be pulled towards 0, for example. So just be aware of that. Just a point or two that's not following the pattern can really affect the correlation coefficient substantially. So some examples. If we have a set of data like this, I've kind of talked about this. The data is in a perfect straight line. We have a positive association. This is a perfect positive linear relation. So R would equal 1 in that case. Likewise, over here in part D, we have the points in a perfect straight line, but we have a negative association. So we have a perfect negative linear relation. And so R would equal -1 in this case. Now, if we have points like this, we have a positive association. It looks to be pretty linear. So we would say we have a strong positive linear relation. So this might be a case where R equals +0.9. Okay. If you look down here, we have the same kind of scenario going on. We've got a pretty strong relationship linearly, but it's negative. So we'd have a strong negative linear relation. So in this case, R would be maybe around -0.9. So I do want to point out that +0.9 and -0.9 really mean the same thing in terms of how strong the linear relationship is. So as a measure of strength of how linear it is, 0.9 and -0.9 mean the same thing. The only difference is if it's positive, then you have a positive association. If it's negative, then you have a negative association. Likewise, here we got somewhat of a positive association, and here we have somewhat of a negative association. So this might be, well, the author calls this a moderate positive linear relation, and this might be a case where R equals +0.4. whereas this might be R equals negative 0.4, a moderate negative linear relation. So again, 0.4 and negative 0.4 mean the same thing in terms of how strong the linear relationship is. Positive just means it's got an upward trend, right? It's positive association. Negative just means we got a downward trend, so it's a negative association. And then, as I've mentioned before, when we have no upward or downward trend, either one, we just have points kind of all over the place, this would be a case where R would be close to 0. And likewise, if I have a relationship like this, there maybe is a relationship, just not linear, so R would be close to 0 on that.